workshop. So our first speaker will be Max Welling, who will be discussing equivariant reinforcement learning. Let's take it away.
All right, thank you. Okay, just to reshare like this. So can you see the full screen now?
Yes.
Okay, how much time do I have again for this?
An hour.
A full hour, including questions, that is, right? Okay. All right. Yeah, so I probably don't need an hour. So this is the first time I give this talk. Might be not as smooth as usual. It's also quite exciting to talk about something new. So I'm going to talk about Equivariant RL. I try to fit it into the theme of the workshop, which is optimization and equivariance. And so this is work with these folks here, in particular Elise van der Pol. So here she is. We have written a couple of papers, and she's been the driving force behind all of this. She is almost graduating, so on the job market, if you're interested in, and with these three wonderful collaborators as well. So I'll start with a very brief introduction in reinforcement learning. Then I'll comment a little bit about, what reinforcement learning really has to do with optimization. Then I'll talk about Markov decision processes, homomorphisms, and their relation to equivariance. And then I'll talk about equivariant multi-agent systems. And this is a picture made, and there's another one coming by Maurice Weiler about actually equivariant deep learning on manifolds, a sphere in this case. Not quite related necessarily to this talk. Okay, so what is reinforcement learning? So in reinforcement learning, we have basically an agent, and we have a world. And the agent can act on the world, can do things in the world, and it can observe the state as well as a reward from the world. And so typically learning is by trial and error. So you have a sort of a starting policy, you try things, you collect rewards, and then you iteratively improve yourself. So in more detail, so we have a policy pi for the agent, depending on the state the agent is in. So in this talk, we'll only look at fully observable Markov decision processes. And the policy is basically a function that maps the state to an action. So the action is then applied to the real world. And then the real world, under the action and given its current state, will then transition to a new state. Could be stochastically, but also deterministically. And then there's a reward that gets collected at that time, depending on both the state as well as the action that's being taken, and that's recorded as R at that time. So those two numbers are then being, under full observability, are then being fed back into the agent, who will then use that to update the policy and choose a new action. And in the end, of course, the agent would like to maximize the total future reward, not just the instantaneous reward. So S are states, A are actions, T are transition functions, R is the reward function, and pi is the policy. And as I said, the goal is to maximize the cumulative future reward, not just the instantaneous reward. Okay, so what is the relationship between reinforcement learning and optimization? So there is a recent uptake in the number of papers that are trying to use reinforcement learning to improve optimization algorithms. And the idea is that you can sort of amortize over different optimization problems. That is, you can sort of look at the patterns that algorithms use to solve certain problems, and then encode those into a policy which could then help you solve the problem faster next time. So we have ourselves worked on something like vehicle routing problems, and TSP, the traveling salesman's problem, is a subset of those. Basically, by having some kind of graph neural network that feeds into state, the current state of the TSP problem you want to solve, and then predicts the next action to take, which is the next visit, the city that you want to visit to solve the problem. Here's another paper, and here the driving.
Max, we have a question really quick.
Yeah. Oh, sure. Yeah.
But could you get back to the previous slide, please? That your cumulative reward, what is that? It's infinite sum with discounting factor or average. What is that?
Sorry, I can't really hear what you said.
Your cumulative reward, what is that? A limit of arithmetic averages or sum with discounting factor?
Yeah. So
Could you define it? Is there a formula for that reward?
No. So there is, of course, a formula, but basically what I'm going to talk about today is sort of independent of what you choose there. Of course, you could just use a discounted cumulative reward. You could choose a finite horizon reward. You could put anything you want there. But basically what I'm going to talk about works for whatever you choose for your future cumulative reward. Is that okay? I can't see anybody, so
Okay.
if you don't agree, then you can say so. Okay, so this is being driven by this student, Wouter Kool, has been publishing on this particular problem, but we haven't really used any sort of equivariance here, although it seems like a very good idea to do it, right? Because clearly solving a vehicle routing problem or a TSP problem doesn't depend on how you orient the problem, right? If you rotate the problem, you rotate the world by 90 degrees, then you would want the same solution out. And this neural network, for instance, wasn't really equivariant, didn't have that particular symmetry encoded in its sort of operations. So that's something that we can still do, but we haven't done yet. But this at least lays bare that there is an interesting relationship between reinforcement learning and optimization. In fact, more recently, Google has written a paper where they use reinforcement learning to do chip design optimization. So putting down all the the memory blocks and the sort of standard cells onto a canvas, such that certain objectives are optimized, like minimum area, yet the wire length should be minimal and stuff like that. So that's a clear optimization problem. And they've shown that by using reinforcement learning, you can learn from previous iterations of solving that problem and do better next time. Now, reinforcement learning is known to be very data hungry. And so here's a couple of examples of, I don't know, number of samples or observations that you need in order to train your policy. And what we're going to try to do today is to use the fact that, in fact, the world has certain symmetries, and that can be used to reduce the number of data points for learning. So in other words, you can learn faster with fewer observations with the real world, by basically noticing that if you have an action in a world, in a certain situation, and you could map that to another situation that seemingly looks different, but you can have an easy transformation on your action or your policy, which still would obviously, under the symmetry, give you the same result, or if it's optimal, that also the optimal result. Right. So here's a couple of examples. So if you change the coloring scheme of your input, your chessboard or whatever, game board, now clearly you don't want the the policy to depend on that. Or if you learn a car to drive in sort of in England, people drive on the left-hand side of the road, and in Amsterdam and in Europe, drive on the right-hand side of the road. You can imagine that there is a mapping between the optimal policy for driving on the left-hand side of the road and the optimal policy driving on the right-hand side of the road. So that once you have learned to drive on the right-hand side of the road, you can then in one go transform everything to a car that drives on the left-hand side of the road. And so you don't have to learn everything from start again. And then of course you can rotate things, right? If you have a task, you pick out, let's say the phone might be your task. You want that task to be independent of the orientation in which, not independent, but, equivariant, as we say, of the orientation in which the task is being presented to you. So in other words, you still want to pick up the phone. Where the action is here at the bottom left, you can transform that action if you know how the world is rotated to the left upper corner. And this one is a pole, and it's a balancing pole, and we see examples about this. So basically, if your balancing stick is like this, you need to push the car to the right in order to balance the pole. And of course, if you reflect that situation, then here you would have to push to the left in order to balance the pole. And so there is a symmetry between these two situations. So we're going to use this concept of a group to reduce the number of transformations that we're going to consider. I think the theory that we developed here is actually more general. You can also think about other sets of transformations, maybe semi-groups or other types of transformations. But to make our life easy in this first sort of setting, we're going to look at groups. We have, of course, certain properties, like there's an identity map, it's invertible, there's closure, and there's associativity. And so a couple of examples are translation, reflection, and rotation. Now, what would these groups and symmetries, how would they work in reinforcement learning? So we have been working a lot on incorporating symmetries in deep learning. So training neural networks that transform in certain ways, or their predictions are invariant under certain transformations on the input, or equivariant, let's say in the case, so invariant if you do classification, equivariant, let's say if you do segmentation. So you want the segmentation map to rotate if you wrote, with the rotation of the input image. But what does it mean for reinforcement learning? So that's the question that we were asking ourselves here. So in reinforcement learning, of course, the MDP is defined by a reward function and a sort of transition function. And what we're going to say is that we want the reward function to be invariant under the action of the group on the state and the action space, right? So in this case, let's say, there could be a symmetry here, and the reward of being in A should be the same as the reward in being in B if you want to go to the goal, because the situation is exactly symmetric. At the same time, there's something similar for the transition probability, where if you apply, the transformation to the input state and the action space, then there's also the same transformation on the transition step, the state where you're going to transition in, and then you want this type of invariance to happen, right? So in other words, this path of going left and then should have the same total reward as this path, which is a similar path, but in this case you go up and right, in this case you go right and up. So there's this transformation between the two. Now, people often talk about homomorphisms, and we will talk about that too. And the idea is that really you can map this situation on an equivalent situation by equating A and B to be the same state. So in other words, you just cut this thing in two, and you map all the states on the left, you map it on the states to the right, because once you know what to do here, you also know what to do here. So you can sort of halve your space, and you can just reason in this space. So we got a mapping, surjective mapping down to a lower dimensional space. Injective mapping.
We have another question.
Yeah.
Max, 1 second.
Yeah.
Like the states in the actions, the same set. So you apply the same group to the states and actions.
Yeah, that's a great question, but the answer is no. So, and I'll get to that in a minute. So, for instance,
it's a wrong formula there.
Yeah, it's true. So this G here, it's sort of a, if I say GA, I mean the action of the group element G on A, which could take a different form as the action of, the group element G on S. So this could be a matrix that is quite different from this matrix, right? So So the equations here are not in that sense super precise, but they mean the action of this group element on this action, which could actually be different than this one. But that's a good
Thank
question.
you.
Yeah. So so we're going to say that SA and GSGA are symmetric state action pairs, and they have the same policy P pi star. That's also an imprecise statement. They don't have the same policy pi star. They have, the same policy up to a transformation, and we'll see that in more detail. Okay, so then in equivariant, so what do we mean by equivariant maps? So if we have some input space, so the space of images of dogs, and we want to map to some, let's say maybe a segmentation map of dogs, then F is the segmentation map, so it goes to a different space. Let's say binary numbers, an image with binary numbers in them. If I rotate the input image, of course I'm going to end up with a different segmentation map, but that segmentation map should be the rotation of this segmentation map. So we have a G here, we have a G prime here, they can be different. And we want the closure of this kind of diagram. We want that first applying the segmentation map and then rotating in segmentation space, or first rotating the input image and then applying the segmentation should end up at the same point. Or you can sort of, here is first fx and g prime equals gx f. Now the special case of this is invariance. So when you are invariant, it basically means that the orbit, which is all the transformations you apply to the input map, is all mapped to the same point here. So you could think of this as a classification problem, where you want to classify this as a dog. Then, of course, all rotated dogs are still dogs, so they map to the same point. And so invariance is given by this equation. Again, this is a special case of the equivariance case.
So Max, just to understand the quantification in your previous slide.
Yeah, sorry, let me actually, so I can see people, I think that's better. Yeah, all right.
I just wanted to understand the quantification in your previous slide.
This one.
So this is, so for all G, there exists some G prime. Is that the equivariance thing, or?
Yeah, so certainly. So for all G, there exists a single G prime that would be the operation on F. And so
G prime is fixed,
yeah, so it's a constraint on F, if you want, right? So G and G prime are fixed, and this means that the map F is constrained.
Should there be a group? Should there be a group action in the image space as well? And
yeah, that's this one, right? G times X is the group action in the image space.
Oh, I mean, I see. Sorry, I mean in the sense of functions, like that's in the domain, and in the range, that's where G prime will act. Really, it's like just a different action of G. But
yes, it's
range.
Different, right? G. So here we actually properly said it was different. It's G prime. I mean, I think I've misjudged my audience because I think I'm talking to mathematicians, and I really have to apologize for sloppy notation. I hope you don't. You can look through it. I mean, this is meant to be sort of a high-level understandable, for non-mathematicians presentation. But it's also sloppy, right? So that's
Would be great to write as a product of matrices.
Sorry?
Would be great to present that as a product of matrices, example of this situation.
Yeah, absolutely. So
product then. Okay.
Yeah, you should think of this as matrices, right? You should really think of X as a, the image pixels written out as a long vector. Huh?
Yes.
Yeah. So think of it as matrices. I think that's the easiest way to think about this. Okay, so the advantages of equivariance when we developed them. So this is not, when we started to develop these things in 2016, we wanted to develop them for deep neural networks. So it was just for maps, predictions, classifications, all these kinds of things. And we did it for Euclidean spaces, but for the mathematicians, maybe it's also interesting to note that we also did it for arbitrary manifolds. So we can actually define convolutions for arbitrary manifolds. And that actually gets into very interesting math because it's fiber bundles and stuff like that. So you can read about it. And this, Maurice Weiler wrote a 200-page document that's much more mathematical on this topic. And Taco Cohen, his thesis is also very mathematical in this respect. So I think that would be a nice sort of reference to look at the mathematics of all of this. But there is very clean, nice mathematics behind this. As I said, so what we want from equivariance is this closing of this diagram, which is first transforming, let's say under a symmetry operation, in this case, rotation over the z-axis, and then doing the filtering, which is like your convolution. In this case, it's some kind of filter that is an edge detector. Should be the same as first filtering, and then doing the symmetry transformation in this new space. So again, this should be phi prime, not phi, because this could, in fact, and I'll show an example in a minute, be a different operation than this. And I'll have an example in a minute. What this does, this puts additional structure on the space of representations that you create, right? Where you're filtering, I hope you know about deep learning, that will give you filter maps. They organize themselves in capsules, what we call capsules. And I'll talk about more in a minute, but under transformations of the input, you'll get very nice transformations in the sort of representation space. Which means that the representation states become much more structured. And again, that's also for the next layer more easy to detect patterns again. It's also for sort of recursive learning, where the next layer needs to learn, patterns of the previous layer. Putting the structure in there actually does help a lot. Perhaps the most important part, another interesting property of these capsules is that they separate the presence of an object and the sort of pose of that object. So these capsules, they have the beautiful interpretation as if you look at the total activation of this capsule, which is the hidden units or the latent units that are in this particular sort of capsule. If you add up all the activations, absolute value, let's say, you'll code for whether there is that object is present. Now, if you actually change the input, if you transform the input, you change the pose of the object, which means that you have some internal transformation happening in this capsule, keeping the total activation constant. So the norm stays constant, but you'll sort of change the phase or the sort of activation pattern inside. And that we call often pose. And that's actually quite related to how the brain also decomposes presence and pose of objects. But the most important part for learning is that this particular trick helps you reduce the number of parameters in your neural network, because it basically, this constraint, this is a constraint on K, the filter, will reduce the number of independent parameters that are in this kernel K. It's similar to if you have a MLP, a multi-layer perceptron, which is a fully connected neural network. There's a lot of parameters because there's n squared parameters, where n is the number of neurons. Where if you make that, where if you exploit translation equivariance, you turn that into a convolution, and then the only set of parameters that is left is the parameters of the convolution kernel, which could be as small as 9, right? So you go from n squared to 9. And so here, if you keep on going, not just translations, but you also do rotations, then the number of parameters is further reduced, with the advantage that you can learn faster from less data. Okay, so then here's more explanation of what this equivariant convolution is, and indeed that the operator that is in the sort of space after the mapping can actually be different from the operator in your original space. So here is Mona Lisa, and this is a sort of in the input space, a rotation of the Mona Lisa, right? So the pixels are just being rotated. Now here is, let's say, our convolution, and the convolution in this case consists, let's say, of two detectors. There's an eye detector and there's a mouth detector. And so you'll get two detections here on the eyes and one here on the mouth. But and to turn this into an equivariant convolution, what we will do is we will copy the filter 4 times over the 4 90-degree angle rotations. And so we get a capsule with 4 elements in them, 4 feature maps here, for both the eye capsule and the mouth capsule. So now how to close the diagram? If I rotate and then filter, it should be the same as if I first filter and rotate. Now what happens if I rotate and then filter? Well, I can see what happens because I now, the eye detectors that are rotated get activated. And so I get 2 detections here and 1 mouth detection here. Of course, all the other ones are out of orientation, so they don't fire. But and here you see that the detections rotate and the feature map permutes cyclically to the right. So now the operation here that's happening in the latent space is not just a rotation of the feature map, it is also a cyclic permutation in the capsule dimension. And this is the capsule dimension. So that's, the best I can do in sort of explaining what, in a non-mathematical manner, perhaps, what the equivariance operation in the abstract space looks like, and the sort of filtered space look like.
So Max, I have a question about this slide. So the group that emerges in this on the right-hand side is a discrete group, and this seems to be depending on what the, so on the left-hand side, it's just a rotation group of, I guess that's what.
90 degrees rotation.
90, only 90 degrees? Or?
Yeah, so, okay, so I see what you're saying. So
Yeah.
this can all be generalized to continuous rotations, right?
Mm-hmm.
And then, this looks clearly different. And so instead of having, sort of the 4 90 degrees rotations, you'll then have to use irreducible representations of the group. So it's much more like, spherical harmonics or something like that. And you cut that off at sort of a frequency. So you say, either you take an infinite set of feature maps, but it's a bit too many. So you'll just take the low frequencies of the spherical harmonics, or, the SO2 rotations, right? Which are just discrete numbers M. And you cut it off to keep a finite dimension for your capsule. And then you'll have equivariance under any rotation angle, and not just the rotation angle given by 90 degrees. But this is just for, for simplicity.
And practice, what would you do? From a practitioner's point of view.
Yeah, it's a great question, because there's advantages to both. So it turns out that if you do a pretty fine sort of discretization of this group, it has the advantage that, the disadvantage, of course, that it's approximate in that sense. The advantage is that you also have to use a nonlinearity after this, and the nonlinearity has to be equivariant as well. It has to maintain equivariance. And in this particular representation, you can use basically a pointwise nonlinearity. If you apply the same nonlinearity at every pixel, it will work. However, if you do this in this kind of sort of Fourier space, in the irreducible representation space, the nonlinearities that you have are much less varied, in the way that, for instance, you can take the norm and take an arbitrary norm function of the norm of the of the vector of activations, but that's about it, because otherwise you will break equivariance, and so that actually hurts performance quite a bit. So it's in fact it's the jury is still out a bit, and I would expect it's clearly a lot nicer mathematically to use the irreducible representations. But there is this practicality about nonlinearities, which make it in practice actually that this might work better.
Thank you.
Okay.
Sorry, Max, can I also ask a question on the input side? I guess these rotations by 90 degree you can represent exactly, and if you have general rotations, then do you do the same thing there? Like you have your input image, you decompose it in some finite number of Fourier modes, so that you then can rotate exactly on the input, or are you treating the group elements as being sort of approximate actions?
No, so what you do is you don't have to decompose the input in terms of Fourier elements. You just can take the actual pixel input, but the kernel that you use to transform to the next layer, that kernel now has to be in, has to set, has to map to an irreducible representation. Yeah.
And that equivariant still makes sense, of course. Yeah.
Yeah.
Thanks.
Yeah. Okay, so the next thing is probably ridiculous to explain to you because you know much more about this than I do. But let me at least state this idea of a homomorphism. So it's basically a map, right, where you take an x and a y in an input space that has a certain product, and you then apply a map f in such a way that you also have an operation in this new space f, and such that this equation holds. And of course, you can do linear maps and maps to exponential functions, but the most important one here are the group representations, which is a well-known homomorphism, which is if I take two group elements and I multiply them, and then take the, let's say, matrix representation of the group element that comes out of that, it should be the same as first taking the matrix of G1 and then the matrix of G2, and then do matrix multiplication of these two sort of representations, these two matrices, these two representations. So this is, so here we go from sort of an abstract group element to the actual matrices, and we indicate that with rho, but we'll be sloppy about it. And if we say G apply to X, then we actually do mean the matrix representation. Okay, so now let's go to how, and this is known. So, there's this particular, for instance, this particular reference here. So it's known that there is, so that sometimes there is these homomorphisms in MDPs, which basically mean that there is some kind of symmetry in this space. So, so let's say this is our input space. It's like a pole balancing task. The space consists of states and actions. And this particular point here is the pole is, falling to the left, and the cart is moving to the right, which makes it worse, I guess. So you could think the cart needs to move to the left in order to balance this thing. Now on the other side, if you do a flip around the origin, then there is another state action pair that is mirrored, and that has the same reward and the same, and it has sort of a transformed transition function. So if I knew what to do here, I know precisely what to do here. I need to transform the state, the action, and the next state, right? And so there's a whole bunch of these things. So what we're going to say is now that we have an orbit of the group which applied to a particular state that goes through all of these elements which are sort of related to each other under this symmetry in this state action space. And what we can do now is under a MDP homomorphism is map them into a smaller space, an abstract space if you want, where we're only going to retain one copy. So it's kind of an equivalence class now. So you're just looking at the equivalence class of states, where the equivalence class is the orbit of the group. We call this S bar and A bar. And we're now just going to reason in this space. So every time I'm sort of moving here and then I'm moving here, now all of these things can be mapped onto each other, and I'm sort of using less data to learn my policy, because I'm just saying that these two policies should be related to each other, through this symmetry. And it's sort of this connection with equivariance that is kind of new in this story. Yeah, so I said this right. So there's a symmetric actions pair. They sort of result in the same policy pi star, but I mean by that actually one is a transformed policy of the other one. Okay, so something like that relates to also what we did in neural networks and deep neural networks. So in a deep neural network, let's say I have an input image and I have a symmetry transformation, say a rotation. So I have this orbit here. And I have another guy here, which is not on the same orbit. There's another orbit. If I have some kind of homomorphism that maps, let's say, these two things to the same abstract sort of icon of a face, then if I move along this orbit and I do the mapping from here, I get to a rotated copy of this sort of abstract representation of these faces. And it's this equivariance which maintains this nice property that this actually happens, so that this face is not mapping to some other abstract space. And you can think of this maybe in this example as the policy that is changing, and this as the sort of input state pair. Okay, so let's look at certain problems, and let's connect the sort of the two issues of MDP homomorphism with the equivariance. So here's a couple of examples that we looked at, for instance, pole balancing, and this is a sort of a the cross needs to catch the this particular thing. So I know this symmetric under rotations of 90 degrees. So they need to it needs to go on top of it to catch it or something like this. And here is a pong, which you can move this thing up and down. You can move this thing up and down. You can hit this ball to move to the other side. And there's also a flip symmetry like this over the image. Okay, so again, the equivariance that we would like to enforce here is that if I have a particular situation here and I have a mirrored situation like this, we apply to the state some operator L. Here we have some kind of policy network. So the policy is a function of S that recommends an action, right? That basically says, this says, high probability move to the left in order to balance the pole, right? And here, the same thing for this one. What we want is that there is an action in this space, or sort of an action of the group on this space, transformation on the policy here, that would then in this case permute the two actions, right? So the policy here is setting high probability on left and low on right. The policy on this side, the flip thing, should be high probability on right and low probability on left, right? And we want that this diagram commute. So first flipping and then and then computing the policy should be the same as first computing the policy and then flipping in this new space, right? And so the action here is a very different action than the action here, because here the action is actually a mirroring of the pixels of the image, where here the action is a permutation of the two dimensions of the policy. Okay, so basically in equations, so I have a SA pair and same policy. So I have a policy. So we're going to look at the policy. We're going to train the policy on a state S. Let me first go here. So if I have a policy on a state S and I transform the state, which is going from here to here, that should be the same as applying the policy, which is going from here to here, and then transforming the policy, which is going from here to here. Right, and these two paths should be the same. So that's explicitly equivariance, right? That's exactly equivariance, but now expressed in the space of state actions and policies. Yeah. Okay, so again, going back to the homomorphism. So here we have sort of our orbits, so the state actions which are related through the transformation to G, the group action G. And here's the sort of mapping to the abstract space. So we now want to create a policy implemented as a deep neural network to enforce this equivariance. So we're really going to work in this space now, but we're going to enforce this idea that these two things are related by this equivariance relationship. And so that's similar to basically acting directly in this space. And we have a way to construct this in a very simple, straightforward manner. I just want to say that this is something that we did in 2016 with Taco Cohen. It's basically called a group equivariant convolutional network. So here it's a neural network which implements these equivariant convolutions and nonlinearities. And the policy is this group convolutional neural network. And it has the property that if I rotate the input images, I will get the right transformation permutation of the action sort of policy. Okay, So now the some results. Well, I don't know. Here's the card poll example. And basically, what you should take away from these examples is that if you make these policies equivariant, then indeed you need less data to train. So you can see that the return rises faster during learning. So it does need to see less examples in order to some actually ends up being higher. And the gain is pretty significant if you just use even these simple symmetries. So the final step that I want to take you through is this idea.
Max, we have a question.
Yeah, definitely.
Yeah, that's precisely where I'm getting. So as a theorist, I'm trying to see where potential gains are. Is there any way I can see anything in rates here? Because I mean, it seems like at best I get a factor of 2 in my sample complexity. I mean, I can just stuff twice as more data, right? I mean, is there any hope to gain more than this? Like, is there any example where you think there would be a non-trivial scaling in the number of group actions you're modding out? Like in the exponent maybe or something?
Okay, that is a question that is made a little too hard because I do think that you're right that, you know, if you mod out, let's say, okay, let's put it this way. So if it's a discrete group, then I guess you can just gain linearly in the number of actions, the number of group elements, because it basically every time you have a group element, you'll fold the space. Isn't that actually, okay, so every time you have a symmetry, you fold the space in 2. And so if you then another symmetry, you'll fold it again. So wouldn't that actually scale quite nicely? I'm not sure. The other thing to say is that for continuous actions, for instance, you map a circle to a point, right? So now all the points of a circle basically all get mapped to a single point. So the space in which you now operate gets quite dramatically reduced in some sense. So I don't know how that translates to rates. I guess you're the theorist who can figure this out. But in practice, certainly this does help a lot.
I mean, if I think in terms of data, I could just do like, so yeah, I could do data augmentation, for example, right? If I observed only one left side of the card polls, I could just basically duplicate all this stuff that I have to the right, and that would have essentially the same effect, right?
Yeah. So okay. So let's say that's that in principle that's true. It turns actually out that data augmentation does not work as well as hard coding it into the neural network. So there is. But that's probably not, another rate, but it's certainly true that actually the two are synergetic. So even if you have hard coded the sort of the symmetries in, data augmentation still helps a little bit, strangely. Yeah, so let's say that if you have, if you have one group element, then, you can sort of, for every point, you can replicate one other point. If you have 2 group elements, then for every point in principle, you can produce 4 points. 4 points, right? Because you can, let's say, translate to the right, translate to the left, first translate to the left, then translate to the right. So you get sort of 4 points now that you're adding to the problem. Now, if you have 3 group elements, I think this sort of scales exponentially, right? Now you can sort of add 8 points.
Yeah, I mean, okay, from a theoretical point of view, the complexity of the positive orthant and the entire space are essentially the same in terms of entropy. So like, even if you divide by 2 to the n the size, like if I fold it, the number of dimensions, I'm not gaining really anything in terms of complexity. So I don't know where I could milk that out in this example with maybe with a continuous one. And can I ask a final question? It's about computation. So the way I see this, when you see the difference between data augmentation, say, or I mean, it's just like, let's say the data is being generated, you don't even need to augment it, right? So like, I look at the card poll, I mean, you play to the left, you play to the right, and maybe you're like, tennis player and your left side is a little stronger, but it's okay. You have a decent right side, and you're going to be able to solve this game. Now, what you seem to be doing is enforcing that this player plays perfectly symmetrically. And so I was wondering if this, it's just like proper versus improper learning. Have you encountered like failure modes where enforcing this constraint sort of makes your computational problem, where you're actually trying to minimize your risk, a little more complex, because you're forced to go only through paths that take you through this purely symmetric models, where if you allowed yourself to deviate from those once in a while, then maybe you would actually converge a bit faster to some optimum?
That's
Is
an
it-
interesting thought. So that's purely on the optimization end, right? So the idea that if you give yourself more dimensions to optimize, then the optimization would go faster.
Yeah, but it's really, yeah,
Yeah.
I'm really, I mean, I'm not saying anything deep here. It's just this, like, proper versus improper learning that, people have observed, computational trade-offs, pretty significant computational trade-offs on a regular basis.
Yeah, I'm not too familiar with proper versus improper learning. So, but we haven't observed ourselves, not in RL, but we have done a lot of experiments with equivariant sort of map to just prediction models like deep neural networks. I don't think we've ever seen that this thing learns slower. I mean, you also, of course, you have a lot of, you can just add the, feature maps at will, right? So you can add degrees of freedom as you want. So it's not that you're limited in the number of degrees of freedom, but you do force weight sharing.
Okay.
And what the impact of that weight sharing precisely is on, on the actual sort of optimization problem. No, I don't think no, we've certainly not looked at that, and I don't know the answer to that question.
One comment about what you were wondering. I guess you could already think of a convolutional neural network as doing this, as hard coding equivariance, like translation equivariance.
Yeah.
And that's, I think, a pretty good idea. Convolutional neural networks saves you, a lot, as opposed to just like having like a dense neural network, like to turn images into images or something. Does that sort of make sense?
Yeah, this is more for a plan. I don't think of convolutional neural network as a parameter saving strategy, right? I mean, it's just hard coding something that you actually want your network to do, and it's very unlikely that a gradient descent would like fill the CNN if you get it enough data. And I think it's just like your stuff. You have images, you start from this thing, and here it feels a bit more incremental than just saying, okay, I'm going to start with images and I'm going to like force some spatial filters in there first, and then go from this architecture. Here it feels like yeah, it's just like little tweaks at the end. I don't know to what extent the trade-off is achieved. I mean, it seems that it's working well, but I can't perceive it as strongly, I guess. Right.
I would guess continuous makes a huge difference.
Yeah.
One way you can kind of think of it heuristically is that like the group acts on your search space as well, and you're quotienting out by the group action. So it's a kind of dimensionality reduction, really, right? Like you would expect the dimension of the search space is going to be reduced by the dimension of the generic orbit. Now, if you only have a single group, then that's only going to give you like a constant decrease in the dimension. But what
A single group or a single one element group, right? Because this, a group can have many group elements in it, right? Or
what I mean is that if the symmetry group is fixed,
yeah.
But what I wonder is, could in this framework, could you also treat situations where the group itself depends on the size of the input? So for instance, I give you an input of size n, and you want to learn like a symmetric function in n variables. In that case, you might expect that the scaling would get better and better as it gets large.
Yeah, well, that's sort of for the symmetric group, you mean, like for permutations.
Sure, yeah.
Yeah, so certainly, right? So the graph neural networks precisely implement that, right? So they precisely implement the symmetry under permutations that, it doesn't matter how many input points you have, you'll implement invariant or equivariant function, actually equivariant functions on the permutation group that are just fine with any input size n. And here, I don't know, yeah, here I guess the group is fixed, so the size of the group is fixed for sure. Yeah. Okay, let me maybe finish off. I have a few more slides, and then we can maybe continue the discussion. So the last part is about multi-agent systems. And in multi-agent systems, the situation is slightly different. In this case, so you can think of, let's say, there's a traffic situation, and you want to, predict, if there's traffic lights here, maybe the traffic lights turning red or green. What we're going to consider here is a joint reward function, so coordination in that sense, but we want local computation. So we want these nodes to locally compute their actions, but coordinate through communication between sort of the different agents. So again, here we have, so this is the sort of the situation I sort of discussed before. So we have, a image, and then we can rotate the image. So you see that not only, so the whole thing rotates basically. There's a policy here for the 4 actions that we can take at these 4 corners of the road. Then there's some kind of permutation. If I rotate this thing, there's a permutation because now this action is going to move here. So this action is now going to move there. So 1's going to 2. So this action, this policy is going to move here, but it's also going to change, right? Because now the situation also is rotated relative. So the actual policy itself is going to change too. Right, so now we're rotating and then computing the policy should be the same as first the policy and then permuting. And the way to solve this is going to be now using a graph neural network, an equivariant graph neural network. So the input state S goes to an equivariant graph neural network to produce the policy pi. So this is a distributed computation. There's basically a message passing scheme between the nodes in the graph. So here are the nodes in the graph. And it has the property that if I rotate the input, I will get the proper transformation on my policy, like here. Of course, it is also equivariant on the permutation of the labels of these nodes, but that's a different thing. Let me quickly tell you a little bit about graph neural networks. Maybe just focus on this side here. This is normal convolution, which you can think of as message passing from your neighboring nodes to the central node, where each node can send a different message, or it has a different matrix to multiply the feature value of the neighboring state, to the central state, and then everything gets added. And for graph neural networks, the number of neighbors can be different, and so you will have to sort of use the same function for each one of the neighbors in order to maintain this property of equivariance. Otherwise, the result would change in the order in which I would treat these nodes, and of course the graph doesn't have a particular ordering, and even the number of nodes can differ. Now, the more general function, the more general way to write this is I have some feature states H and at the nodes, so HI and HJ, let's say, and I have some fixed features living on an edge. They go through some function. If it's a fixed function phi, to compute a message, the message that goes from I to J. Then we are going to collect all the messages that are flowing from the neighbors into J, which is sort of the summing operation here in the middle. So we're summing all the messages going into the central node. And then we have another fixed function, could be neural net, that takes in the message, takes in the state of node J, plus some additional fixed information that's living on a node. Again, through some function phi to produce the next feature value t plus 1, and then you iterate this process. So that's a graph neural net. So what we've been doing is to make this graph neural net equivariant under rotations, because that's what we need for the for the RL problem. So here we have our little graph. On the graph we have scalar information and we have vector information. And what we want is that if we rotate the graph, so here's a rotated version of the graph where this x4 flows all the way down there to here. Of course, the vector rotates as expected. The scalar features don't transform at all, right? So that's a rotation of the graph. And we want that first filtering, filtering changes the positions of the graph and the vectors on the graph and the scalar features. First filtering and then rotating should be the same as first rotating and then filtering. Now, here's more detail on this message passing update. See, I have a little bit of time, so let me just go through it a little bit. So now here's the message. Now, the message not only depends on the scalar features of the neighbors, but it also depends on the distance of the positions xi minus xj. That's clearly an invariant. And then we compute some velocity vector, which is a linear combination of two vectors multiplied by scalars. We do an update. we collect the messages, we do another update on the node. Now this turns out to be, I mean, it's easy to see that this is equivariant because the only vector quantities, which are v and xi minus xj, are simple, you know, three-dimensional vectors that get multiplied and combined with scalars. So this thing is still a vector after you do that. Now we've extended this, and I won't go into this. You can look up the papers here. There's this called SC3 transformers, which actually something very similar that's being used for AlphaFold as well. This is the later steerable equivariant message passing. It's based on spherical harmonics or irreducible representations of the rotation group, so much higher order representations. And sort of here's a nice sort of demo of here's the graph. So these things are sphere, you know, functions on the sphere, and in some bizarre way, you know, they're visualized by, you know, by these blobby natures. I think, you know, the actual value is sort of how far it sticks out. And it changes because it's going through the neural network layers as it's being processed. And if you rotate this object, you know, everything will precisely rotate the way you would imagine it should rotate, right? So this thing will precisely rotate with the actual three-dimensional object, and that's constructed that way. It's not trivial, but it feels trivial, but it's not trivial to construct it that way. Okay, so then to conclude, so I should say that these things are now the actual equivariant graph neural networks, right? So this is this object here which computes the policy and therefore is equivariant. Okay, so to conclude, now we exploit symmetries in reinforcement learning and MDPs because the agent can then need fewer experiences or interactions with the world, or have to collect less data and interactions with the world to perform well. There is a nice relationship with older theory, which is on MDP homomorphisms, and it's basically that the homomorphism is a equivalence class over the orbit of the group. This is one of the first papers, you know, on how to, you know, connect equivariance with sort of reinforcement learning. In the sort of distributed nature for the sort of for the multi-agent setting, we have a sort of formalism that works with these graph neural networks where we compute locally but coordinate globally. So we have a global reward function, but the agents compute locally what they need to do. And then I would say, to reiterate the relevance to this workshop perhaps, is that in reinforcement learning, there is this, you know, is a tool that is starting to emerge to learn to optimize, right? Not just to have some kind of, you know, fixed optimization tool that you have to run again and again and again. It's more like meta learning, where you, you know, you look at many problems in the same family, you try to extract patterns that you then use to search faster in the next iteration of the problem. And what hasn't been done, in my opinion, is that you can use the tools of equivariance and symmetries to solve these problems faster if you do this in this kind of meta learning sense. So in other words, you know, if you want to solve this TSP problem, it should give you exactly the same solution as if you would present the cities in this rotated form. So any policy that would guide you through picking the next city should in fact be equivariant, and you know it's equivariant. So if, you know, one city is presented to you like this and the other problem is presented to you like this, you should really, you know, this policy should learn that it's actually trying to learn the same policy but a transformed copy of it. And that's where I will end. Thank you.
All right, thank you, Max. Are there any questions?
Hey. Quick question. So I have a question about approximate equivariance. So whether I should think of it as a good thing or a bad thing. So here it seems that since you're enforcing, you know, strict equivariance, and that's what you're implementing, it feels like, you know, maybe there would be a stability study to near equivariance, but it would be thought as a negative thing, some departure from your assumption. And so you would maybe try to show that in fact you are, say, robust to slight deviation from this equality of equivariance that is imposing on you. But you know, and I agree,
Yeah.
you know, algebra is all about equalities and, you know, love this, but I'm not an algebraist and I love inequalities instead. And rather than imposing equivariance, I would like to impose some sort of, you know, smoothness along group actions. Okay. And that's something that could actually go way beyond the exact orbit that you have. I could just say, you know, I'm sort of Lipschitz in the group actions or something if I have a continuous group. So, you know, if I do a small symmetry, then I'm close. But if my symmetry, if I do a small group action, I stay close. But if I do a large group action, I'm not that close. So think of like maybe like a 6, right? So if I take the number 6 and I start rotating it at some point, I'm not going to call it a 6 anymore, but close enough, I still want to call it a 6. So
Yeah, I
are
totally
there any
understand.
studies that are there any ways that is this framework allowing me to accommodate this sort of
It is.
smoothness? Okay.
Yeah, there is that. I think that, you know, a lot can be done there, but one way that you could accommodate it is by, instead of forcing it the way we do it here, you can put a loss function, an equivariance loss function on the problem. So you can basically say, I believe there's an approximate equivariance, and so I want, you know, the input transformed and then filtered. I want that to be penalized from, you know, first filtering and then transforming my representation, and I can choose the penalty that I put on that violation of that equality, right? And so by using sort of regularization terms of that kind, you can certainly deal with approximate equivariance.
Okay. Thank you.
Okay, we have another question.
I'm wondering about the.
Do we still have the speaker? Yes.
No, there was a question online as well. So.
Oh, okay.
But you can go ahead. Yeah.
Okay. I was wondering about data augmentation. I guess when in just the classification setting, it's kind of free to augment your data. You don't have to go gather new data. But in RL, like I can imagine, like if you're trying to train like a robot to pick things up, you actually have to like have it run on the, you know, the rotated like stuff. So is data augmentation no longer free in the in RL, or is there still some way to do it for kind of free?
So I'm not an expert in RL, but I think once you have, you know, the full experience for one input, and you can sort of, you know, in silico make the transformations and do your training, assuming that you can sort of, you know, take the input, but then you transform the input under your group action and, you know, transform all the other, the actions as well. I think, okay, let me think about that. So, okay, so that's for equivariance. Now for, yeah, I guess you're right. So if you would transform the input, you would have to go not just through a sort of a classification, but you would have to go through maybe even an action, right? And an action might actually be quite expensive in that way. And so it's much better to build it in as a constraint rather than do the augmentation, because it's way more expensive. Yeah, I think that's right.
Okay, thanks.
You can
go for the online question.
Just go for the online, and then we have another one in the audience.
Yeah. So I have a very simple question. So all this.
Sorry, let's take the question from Soledad. Can you unmute yourself?
Okay, thanks.
Yeah.
I have two questions. So the first question is regarding the group equivariant convolution approach, like versus the irreducible representation approach. Would you say that the first one makes sense when the group is discrete because you have to do an integral, and the second one is what you would use for general groups? Yeah,
so I think so. The group equivariant is certainly most appropriate for discrete group, but you can also do it for continuous group by simply discretizing the group, which is of course not ideal because you'll be approximate. So it can actually be used for continuous groups. People have done that for a rotation group. They've simply discretized the angle. So the irreducible, you do need to, the problem with the irreducible ones is also that you do need to know the representation theory for that group. and I'm not sure it's always known, right? Although there is quite nice, yeah. So I guess you do really need to know the representation theory for that group. So yeah, if the harmonic analysis isn't completely worked out for your particular group, then you're a bit in trouble there.
And another question is, would you consider using constraints coming from units, from like dimensions, like say if you're doing some physics simulation, some constraints coming from just doing computations that respect units? Is that something that people care about?
So what was this thing? UNet?
Units, like if you have something, some things that are like kilograms or meters, and you want to have a prediction that is an energy, would you care about making it so that if the model respects the units? Is that something that people care about?
Well, I haven't cared about it, but it's an interesting observation. So we typically don't care about units in computer science, but as a physicist, you would care about it. So you could demand something like, I want my predictions to be equivariant under changing units, right? So you could say if somebody else decides to use inches instead of centimeters, I still want my answer to make sense, but now, you know, in whatever, you know, units you want at the output, and make it. And so in other words, if you expect that in the future people will change units, you'd better make your neural network equivariant against those changes. If that never happens, if everybody agrees to use the same units, you don't have to do it. But I agree, you can certainly think about units as a way to make things equivariant. Yeah.
Okay, I think we'll have one more question and then we'll wrap up.
So I was curious actually about your answer to a different question a little bit ago. You were talking about approximate equivariance, and you mentioned the possibility of penalizing non-equivariance or non-invariance. What I'm wondering is, do you know of a way to do that that's actually computationally efficient? Because naively, it seems like in order to implement that kind of penalty, your cost function has to involve computing an integral over the group orbits in order to determine how much the function deviates from its orbital average. And it seems like that would be extremely costly because you're doing an integral in a high dimensional space. Is there a way to actually like do that efficiently?
I don't think you need an integral actually, because the idea is that let's see. I mean, you would have to do something like data augmentation, right? So, but you can sample that orbit, I guess is what I want to say, right? So you can sort of sample points on the orbit and force, you know, basically do backpropagation. And in your backpropagation, make sure that everything that is sort of sampled on an orbit satisfies or approximately satisfies that equivariance loss function, or where the equivariance loss function gets minimized. And by sampling it, I guess you don't have to integrate over the orbit. That's sort of a practical way you can sort of do it, I think.
Thanks.
All right, well, let's thank Max again. Thank you so much.
Thank you.
Let's take a coffee break and hear from Soledad next.
All right, bye-bye.
Thank you.
Thanks very much.